So thank you again for this kind invitation and opportunity. And I have only one slide on sensing because I'm not the expert in that. So some of you saw me at the panel yesterday. So I'm Mariam Kiran. I'm the group leader for quantum communications and networking. We sit in the quantum information science, and key thing to see is that this sits inside the computer science division. So we're all basically computer scientists and mathematicians trying to solve this problem. So Bert did a very good introduction to quantum, and he did mention that networking seems to be more of an engineering problem, and I completely agree with him. And that brings in a lot of new kinds of opportunities for all of you to also help us, and a lot of room for collaboration. So this is the outline I'm going to be following for today. So I'll start off with an introduction, going into why DOE and quantum DOE is interested in quantum and what kind of applications we're thinking of from a networking perspective. And hopefully this gives you some ideas on how different kinds of sciences are also looking at deploying quantum devices in their infrastructure. Then I threw in a few more examples on quantum sensing and how SIAM community can actually contribute to some of these applications. And the final examples on certain takeaways that people can start working with. So I actually don't see the slides here, so I'm going to be constantly checking over there. So, right, so starting off with engineering challenges. So my own research for the last 6 years, I've been developing this new research area of developing self-driving networks, and that has led me to discover a whole lot of new research ideas in AI and what kind of AI techniques are actually suitable for networks. So working very much with wired networks, such as the internet we deal with, routers, switches, etc., wireless networks. We've developed, and Bashir, who's here, was actually part of the project, developed some of the deep learning methods for traffic prediction in the future, so you can actually do optimization based on where you think that network is going to be congested, or you could build some intelligent controllers that automatically reroute traffic as things change. And essentially what it all boils down to is a network is a graph. So think of everything as a graph optimization problem, and you're optimizing under constraints. So that's purely a SIAM kind of problem, and we've been reading a lot of your papers to help us design these things. Now, quantum networking actually is a little different from those traditional approaches because we're also doing the fundamental physics along with the engineering in this case, because everything is new, we're still developing these things. In terms of fundamental physics, there's a lot of critical components that need to work in our labs, level 0, level 1, such as how do you generate a qubit, which is a good quality that can move down the network and not lose its state as it goes down. So those are critical physics problems that we're looking at. And then from an engineering perspective, you're working with the fiber infrastructure that already exists. So now so a lot of our internet is provided by these big companies, Verizon, AT&T, and they own some of the fiber that is on the ground. So if we want to deploy quantum on this, we actually have to go and talk to them. And they will sometimes give us access to their small shacks, which they call, where they've deployed all their equipment. Sometimes not, because they don't want to risk it going up on fire kind of situations. So you have to be very, very tested and thorough before you start approaching them. And that introduces another kind of engineering challenge because we don't have fancy labs where the quantum network is actually going to be deployed. So we have to think about how the real world deployment is going to work. So I mentioned yesterday that quantum network is actually not going to be a replacement for our current internet. We have great systems, they work very well. For a lot of the problems we have whole economies built on the way we do internet nowadays, but it's going to work alongside it. So there are some applications that are more suited for quantum networks, which we'll go over. And that is where we think that quantum networks is really going to make a game-changing capabilities for science discoveries. We're going to have hypersensitivity in quantum sensors, and how is those going to be networked to get more science out of the applications we do. A large issue with all of these is having access to testbeds. So I mentioned that it's an engineering problem. So if we do have access to actual hardware where you can design your algorithms and test them out in hardware, because a lot of the times things work in simulation 100%, but when you move it to hardware, it only works up to 80%. So how can you improve the 80% up for the quality as well in real life? So there is a number of simulators out there, and people are using that, and that is great for starting, but eventually we do want to move to hardware deployments, and having access to test beds is key, and that's what we're trying to do in the DOE system, build these test beds for researchers to come in and develop their own techniques, and also for companies to come in and test their own equipment on these things. Yeah. So quantum networking, actually, you can think of it as 2 points: quantum computing, quantum communication, and quantum networking. So I have this big diagram over here of building the quantum internet, where I'm not a quantum computing person, so you guys can help me fill in more of those words over there. And then quantum networking, I added everything I know about. But you see that there is some things which are common in both of those elements. So the qubits, and we had a talk where we mentioned that there is superconducting, there are trapped ions, there are material ions. So there are different kinds of qubits which you can work with based on the applications. There's quantum physics, specialized hardware, noise, quantum error correction is also a problem for us in networking. So, and especially as we progress, there is an interface between classical and quantum. So how are those going to be designed is also something which borders in quantum networking as well. So we're learning a lot from the computing community over here. And then in quantum networking itself, we're more focused on what kind of applications can be done. Entanglement distribution, how do you link different sources together, and how do you actually teleport one qubit to the next? And then what is the future quantum internet going to look like? So in our current classical internet, we have a predefined 7-layer OSI model stack. If people know, you have a TCP layer, which helps you identify that the flows have reached the destination and everything is good, and you get an acknowledgement back. That doesn't translate in quantum. So we're having to redesign what the layers of the TCP are going to look like in a quantum internet setting. And this requires skills from all over. So I would really encourage, if anybody is inspired by this, to reach out despite of your skills, because we can always find places where we can work together. So quantum networking at ORNL has so a lot of this work was done before I joined ORNL, so this is my group's work, where they've been deploying a quantum network at the lab itself. So this is their first version, where we have Alice, Bob, Charlie, and Dave across the different computer science buildings shown over here. And they deployed a quantum local area network and started to do these experiments. So basically what it is that you have an optic infrastructure below, which is the fiber which you work with, and then you can imagine qubits or quantum devices sitting on top of that. So you're still essentially using the fiber infrastructure below. Why do we want to do this in the DOE? So there's been a few interesting reports that have been published, so I recommend these, the strategic vision for quantum networks, as well as the workshop, which showed like what kind of use cases quantum networks want to target. So we see that there's going to be upgraded detectors, like high energy physics or biology or chemistry are going to be installing these very advanced detectors, such as quantum sensing, and a lot of these will have quantum capabilities. So they will have high precision data that can give you more science from what you are trying to analyze here. And that is one of the major DOE. So DOE has always been interested in science use cases. The CERN is a great example for that. So detecting gravitational waves across the world can only be done with quantum sensors. But then you have to build a network around that, because you need to connect the data which is coming around. And that is where quantum networks is going to become interesting. The other aspect which we've seen over the few days is that quantum computing itself is very nascent, and if we want to think of scaling quantum computers, quantum networks are essential to that, because you can have limited capabilities, but if you can link those two together, then maybe we can have much more computing power available to us, similar to how HPC started, right? So since the initial deployment of the quantum network at Oak Ridge, it's kind of grown. So we've reached out to our neighboring campuses and we've deployed dark fiber over there. It now runs up to 300 kilometers, and all of it is controlled by classical networking equipment. So these are Palo Alto switches or Cisco switches, which we've bought, and then we've tailored them to control the quantum network below. So you still have physics running on it, but then the conventional nodes control everything. So a better diagram of this is shown over here, which also lists the different buildings which are linked. And basically, it's an engineering problem. So based on wherever we got access, we added 15 kilometers, and then we looped around the whole lab to get a complete 300-kilometer testbed. This is, at the present moment, the largest testbed in the US, where you can actually do quantum networking experiments. And the kind of experiments we've been doing is quantum key distribution. So we partnered with the electric companies to do smart grid over fiber and free space as well. And we are developing a lot of our own QKD devices. So these are called Alice and Bobs, and having FPGA engineers join us is something we're always looking for. A very key experiment we did at Oak Ridge was called squeezing. So basically what it means is that you can superimpose qubit channels on top of optic channels. And this is going to be a game-changing technology, because you can imagine that whenever quantum networks become ready to be deployed, you will not have the capability of deploying dark fiber everywhere, because you need to work with governments, and that's a whole lot of other problems. So allowing squeezing to become normal, we could actually use the infrastructure of the internet as it exists today. So that is why we're very heavily invested in doing better control over that. And developing other physics, and we're also part of the Internet Research Task Force to actually go and talk about some of the technologies we're doing so that we can be part of the standards that come out of this. So some of the physics I added over here because, so there is discrete and continuous variables, and possibly the physicists here know more about this than I do, but we look at both of these kind of variables because we found that some applications work better in certain things. So discrete is basically just your photon that you can measure as a Poincare sphere, and you can do some sort of polarization and those kind of techniques. So such as the source optimization, you could do that. But if you want to also represent the light as a wave, as a continuous variable, you can have amplitude and energy and time also represented. And this is more suited for some other kinds of applications which we want to do. This is just a slide to show you how squeezing works. So this complicated diagram over here, done by Joe in our group. So basically, it's a whole lot of FPGA, and I know that it's difficult to read, but what you see here is that these are actually distributed across 3 different rooms. So you can create a source, which is located in one room, and have those 2 detectors in 2 other rooms, and then add distance in the middle, and this is how you actually start building a quantum network. And there's a lot of physics that went behind this. It was not an engineering challenge, but this is what allows us to achieve that squeezing technology we're talking about. And some of you guys would recognize this. So we were talking about lasers over the break. So this is, you would know that there is 1560 is the midpoint over here, and everything on this side is called the signal, and everything on the other side is called the idler. And this is how we build a quantum network. So you have a laser pump, and you have a polarized entangled source, which allows you to generate photon pairs. And then you run it through frequency multiplexers, which allow you to select certain bands on the graph shown above. So anything you select on the C band, the opposite is going to be on the L band, and that is how you can select the photons going to different rooms. So Alice, Bob, Charlie, Dave are representing 4 different rooms in this diagram. And you can, as a result, have an entanglement between either Alice and Charlie or Dave, or Bob and Charlie and Dave. And this is how entanglement distribution works, where you have to have a pair of photons that you then deploy. So one of the major challenges in networks is that entanglement does not travel far. So I added this example of distances just to show you what the current state of the art is. So in 2023, which is last year, they deployed this experiment of entanglement using trapped ion. The maximum they went up to was 50 kilometers. There have been some previous experiments where they've done free space communications using satellites, and that has gone up to 144 kilometers. And the famous experiment by China in 2021 shown at OFC was 4,600 kilometers, and they used satellites to connect Beijing to the rest of the cities in China. And that is what we're trying to compete with, so that the US can have this. And one of the problems is that the photon loses its strength as it passes through the fiber, and that's why satellites can actually give you more distance because they don't have to deal with the friction in the air and stuff like that. And quantum repeaters is a technology that is also being implemented to help you add more distance to this, and they use entanglement swapping to do this. So the quality of the fiber really impacts the photon traveling. And again, we have no control over this. If we're talking to the Tennessee Valley Authority to give us fiber in the ground, we don't know what kind of fiber they will give us, or AT&T what kind of fiber they will give us. So we actually can only run experiments after we have access to that fiber and what kind of equipment we could put on that. So how do you improve loss or error correction as the photon travels down is something which we are very interested in from a physics point of view. And also having maybe quantum memory, how do we improve the loss, and new routing algorithms. Again, this all becomes a graph optimization problem, especially now with constraints of distance, that how can we optimize the qubits that are traveling across. I mentioned satellite communications, so this is a slide just to show you how we've been experimenting with this in simulation. So a lot of simulators exist out there where we've imagined what a satellite communication between Chattanooga, Oak Ridge, and maybe Tennessee Tech would look like, and all are 100 miles apart. And you can run these simulations to actually find what is the optimum number of satellites you need for having a complete coverage, 100% coverage throughout the day. One thing I learned through this experiment is satellites usually come over you for just a few minutes, and then they go around again, so you lose connection. So you're actually trying to work out what is the best number of optimum satellites to have a constant connection. And again, trying to do entanglement distribution, or QKD, is something we're looking at through this. So quantum key distribution, as we had our friends from the bank mention it yesterday, is one of the key applications of quantum networks. I want to mention the EU Open QKD project that is currently active. It's amazing work they've done. They've actually built QKD small networks in each of the European states, and now they're working on joining all of the QKD networks together. So you can imagine they're doing this for European IDs to exchange with the government, and all kinds of medical data that is going to be shared from one person to the next using QKD secure systems. And they've worked with companies who build their own Alice and Bobs, deploy it on their network. They have their own dark fiber, which they are working with. And they are trying to solve a lot of these problems of building that QKD thing. We don't have such a system in America now, but I think we should be working towards this, because this is really going to help quantum networks take over, especially in the energy infrastructure, which are ripe use cases for quantum security and trusted relay, especially with the cyber problems we have nowadays. So there are fundamental problems for maths in this area. How do you work out the best quantum random numbers for your security? How do you do the secret sharing, the quantum digital signatures? And these are cybersecurity problems, which we don't deal with in networking. And maybe the SIAM community has a lot of techniques over here which we can learn from. So this is another area of cybersecurity researchers to come in and help us with. So quantum sensors, the famous application which they asked me to add this on. So basically what quantum sensors, as I understand it, is that all of your detectors are now going to be replaced with quantum detectors. And these are not small devices. I've seen them in our labs. They're huge, like tabletop experiments. And they basically have very low sensitivity, so people have been using that for temperature detection, pressure detection, and they're not easily transported as well, so they're still trying to work out how these can be actually deployed in the wild. Right now, they work in very ideal conditions. So having those and then having them as networks is one of the challenges that we're working on, to have a network between that. One application is that as they detect something, the qubits are converted using a frequency modulation. You can convert the qubit into an optic, and then that becomes easy to traverse data over a classical network. So that involves using transducers or other kinds of translators in the middle that can do an efficient conversion. And that is, again, an open research area because none of the transducers that exist today have very good conversion rate. So the experiment done by Google showed a 60% good conversion rate. And some of the experiments I've been involved in have started using AI to do an improved conversion rate. So there is another application of AI over here, or maths, to actually help you with build better transducers, because transducers and memories are going to be also something which we will be deploying in the quantum network. Other examples of SIAM applications, so I added the Bayesian state estimation here. So again, when photons are produced, there is a lot of uncertainty in the state. And how do you know that the quality of the photon is good? Because again, our network quality depends on the photon being produced. So we've been experimenting with a lot of Bayesian quantum state estimation techniques, and a lot of the code is written in MATLAB. And actually writing it in Python would really make things easy, because then we can interface it with a lot of our devices. So that is an area of interest that we're looking at. One way of looking at it is if we can add machine learning to it. So machine learning can train and actually improve the quality of the state being estimated. That is something which also is an open area of research. So I'm trying to show examples of how AI and machine learning can actually help build the quantum infrastructure here and give you some more ideas on how you can bring some of your maths into this. This is a very cool experiment, and it's by one of my post-research scientists. So basically what we have here is that we have a source, which is called the erroneous input over here. And then they're trying to detect what the quality of the photon is. Either it's the horizontal or the vertical element of that thing. And what he's trying to do is that he's trying to add real-time control, so basically tune the photon to improve the quality of being produced. So that is shown by the red circle over here. And now, so all of this is done in MATLAB, and he's run simulations and simulations, and theory-wise, this is a theoretical problem. Now what he's trying to do is to see if we could replace that black box with an AI-controlled box that could do the tuning itself. So then he doesn't have to sit and do the hand tuning of these things. Again, from a commercialization point of view and from an automation point of view, if these kind of things exist, you can think of scaling the network would be very easy for us. So always these kind of techniques would really help us go forward. So these are another examples of how we can bring in maths to actually improve the infrastructure. And then finally, we have the protocol stack. So the TCP/IP, or the OSI 7-layer model, which is a traditional stack model which you guys have seen. So we know that the routers and the switches we deal with, so they take in data at the physical and the data link, and then they decide where the packets have to go at the network layer, and then they do the sectioning off of you go there, et cetera, based on the application you're working with. This stack is going to change in the quantum world, because we have to reimagine what qubits are going to look like and how are they going to be decided that which way qubits are going to go. So this is an open area of research. Anybody can basically write a paper and have their own suggestions that this is what the stack should look like. This is an open area of research. And it's interesting for people to see because it ties in everything. It ties in from the application down to the bottom to see how networking would actually be scaled up as well. So key takeaways. So general applications of quantum networks. So I mentioned that I always think about how my work is going to have an impact to the average person. So thinking about the applications that the quantum network is going to use is the first thing. So quantum key distribution is what everybody is doing. Whoever starts with a quantum network will first do a quantum key distribution, where basically you're securely sharing encryption keys. Quantum sensing is something the scientists are interested in, magnetic fields over large distances with high precision. And distributed quantum computing, so actually connect geographically distributed quantum computers. Even in, quantum computers are expensive, so we cannot imagine that one lab will have access to all of these. And then finally, I met someone who was also investigating a secure central quantum computer. So kind of thinking about the Netflix kind of model, because you have security challenges if all your movies are held on one server and people are trying to access it. He's trying to push this idea that the Netflix would have a quantum computer which you would connect securely to, so that you can have a quantum key distribution with all the clients. So you can see all of these kind of ideas popping up, which will eventually lead to new economies forming in the quantum space as well. There are a number of testbeds out there. EPB's quantum network deployed in Chattanooga is actually the only one where you can take in your own device, connect it, and do some real-world experiments on what a quantum network looks like. It's a small testbed, but you can actually do real experiments. And then we have the Oak Ridge National Lab, but there are other testbeds which other labs are also working on. Since we're in DC, the DC QNet is actually very good as well, so we're actively collaborating with them, and that exists here in Washington, DC. So all of these sources are online, so if you need to read more about it. And then finally, the simulation toolkits that exist for research. I found about 15 different toolkits that can model quantum networks. Not all of them are good, but based on what you want to do and what kind of protocols they're supported, and all of this are still in development. Everybody wants to have their own flag in the ground. So there is a lot of opportunity. If you don't have the hardware, you could actually start with simulations, start designing your algorithms, and then start approaching testbeds if you want to transition into hardware. So I'm just over time. So quantum networks are essential for progress for quantum computers. I see this that they have to go hand in hand. It's sad they always get ignored, but quantum networks are the Christmas elves that are always working behind the scenes, right? So you need a network to work. It involves multiple skills working together, and hopefully that this has inspired some of you to come and work with us. And patience is key. I've been in rooms where sometimes you don't want to look stupid, but you have questions. So I would suggest that keep asking questions, because no questions are stupid, and you're learning through this process, because this is a new field. And when I started my research, somebody told me that it takes 3 years to become an expert in a new field once you start. So give yourself time, listen to the others, understand each other, and learn from them. Having internships is a great opportunity. So we have SULI and graduate research internships that are available to students and academics to come and gain experience. And we also have open positions at Oak Ridge, research scientists all the way up to postdocs. If you are interested, please reach out. And this is my email address, so I'm happy to hear what you guys think over the break. Thank you.